Então, a gente vai começar hoje a parte número 3. A gente já começou a fazer a introdução ontem. E vou fazer uma introdução de novo para as pessoas que não estavam aqui ontem e esperando as pessoas que vão chegar. Todo mundo estava aqui ontem? Tu estava aqui ontem no final, eu acho. Tu estava, então tu viu essa parte, né? E vocês dois estavam aqui. Só o professor Fabiano, que não... Do you have questions about the yesterday course lecture? No? So this part was about microgrids. So we are entering in the application. So the main aspect of the microgrid is that it's a cluster, interconnected cluster of sources, storage, charge, that can be connected or disconnected to the distribution grid. Okay? So there is different level of powers. You can have just a house, a battery, and just a solar panel. That's already a microgrid. But it also can be a university, an hospital, a small part of one town, okay? Bairro. And we said that microgrid, so there is, actually in microgrid there is nothing that is macro, okay? Once I made a presentation about microgrids to some physicians. And physicists, when I say microgrid, say, what's micro exactly? What's 10 minus 6 order of magnitude? And I was, oh yeah, I've never thought about that. Yeah, there's nothing macro. It's just because it's a little bit less powerful than the distribution network, okay? So usually we said that it's between 0 and 50 kilowatts of power, about that. There is some hospitals that need a little bit more, and we still call them microgrids. So the main aspect is we can put some more renewable energy. So the integration. There are a lot of technologies, different technologies of solar panels, of windmills for small power, and there is a lot of different topologies depending on the application. Okay, if there is an hospital, it's different from just an house, etc. The organization of the microgrid as an interconnected cluster make the it is easier to control the energy quality. In energy quality, I'm talking about voltage, balances between phases, etc. There is some other issues like access and privacy. So there is a lot of research in that purpose, and there is a lot of users, association of users that tends to fight for their privacy and data. And our part, actually here in this course, will be more about energy management, okay? Usually when we talk about energy management, we talk about the management of energy, the dispatch of each unit, and it can be local, so every unit can optimize their own behavior, or it can be local. In this illustration here, I put it a master that it tends to be general, okay? And what does this master do? He basically optimizes an objective, okay? So now you are familiar with optimization, you understand that we will be talking about objective, constraints, and variables. This objective for the microgrid can be economic. So usually the first thing we're thinking about is economical optimization, because we want to minimize our bill, okay? But we can also considerate ecological assessment of the microgrid. Is the introduction of renewable energy tends to decrease our consume of CO2 or gas emission, greenhouse gas emissions. I didn't put it here, but we can also think about social access, social assessment of the microgrid. Is the microgrid better to increase the access of energy for everybody? That's a question as well. So the main bottlenecks here, I told you yesterday, this is a multiphysic problems, and the time scales comes from the milliseconds for the controller, inverter, etc., to the lifetime of the system. Okay, and we will be looking at energy management level. So a time scale about minutes, 10 minutes, an hour, or a day, or a week. Okay, so between some minutes to weeks. Okay. The geographic scale, as I said, can be really small. We can look really deeply on the chemical of the battery, so it's really small, to something big, like I said, an hospital or university, etc. And here, in this part, we will be looking at big scale, like the scale of the dispatch of energy, okay, in the building or in a small university. In the example that I will talk about in the following, I took an example of a university in Paris. So we have some project about the École Polytechnique. I don't know if it's quite famous in France, but I don't know if you know it. One of the best engineering school in France. It's a military school actually, and they created a new building, and we have some measurements, and we are doing a project of energy management of this building. So I took the data from them, and we will be looking at the energy management we tend to apply to this building. I think yesterday we didn't go there, so here becomes the issues of the microgrids. So there is a lot of different issues in microgrids, and this is not an exhaustive list, and you maybe can add some other problems related to the agération, decentralized power production. So the main issue is the intermittence of this renewable energy, but also the uncertainties. This is in French, sorry. So basically, if we want to make a good energy management algorithm, we need to know what's going to be produced in the next day or next week, and this is not certain. Okay. This is the management problem. So the management problem, we will be tackling that. We will do optimization to do the management. But there are also other kind of problems like sizing or technology that can be handled using optimization. We will see an example of that as well. So the sizing is which size my sources will be. Do I need to buy a big battery or a small battery is enough? And technology is which battery I use, which motor I use for my windmill, etc., etc. And those two last issues can be inserted in optimization problem. Considering the loads, the increasing of the loads can induce some issues in the microgrid. basically on the power quality, voltage issues, etc. And the intelligent management of the loads can save us some money or some CO2 emissions. And there is a problem of peak shaving, demand response methods, and the interface is human and system. Interfaces is more the way we are willing to induce a change of behavior of the users, okay? In which way we will tell the users not to load the washing machine or etc. So there's a lot of research actually on the interfaces, and I will give some details later. The storage, so the energy management of the storage is one of the main issues that we will be seeing. The sizing and technology, that's actually the same for power production units. So this three will be tackled using optimization. The distribution grid, the connection to the distribution grid is usually where we put the meter, okay? And this meter will measure the consumption of the microgrid, and depending on your contract, you will have to pay a bill. So there is some studies on economics, but also communication with the new technologies of intelligent meter. And the sizing is, you can usually, I don't know in Brazil, but I think it's the case, you can choose a different contract based on your power, right? You can say I'm a small consumer, so you will have a small bill, etc., etc. Basically, it means that if you are a small user, you won't use the distribution network as much as a big consumer. So you will pay less because of that. And the main issue of the centralized master, which is here, it's also the interfaces. How I will be communicated from the master to the systems. So what's the communication between them? How do I give orders to the units? And how do I communicate with the users? Okay? How can the user interact with the management system? Basically, the centralized master is responsible for forecasting. So I said that we need to know the weather of tomorrow or etc. So basically the power production. And he will be responsible for energy management and energy dispatch. Okay? So in the following, I will be looking only on the energy management problem of the microgrid. I will not be talking about management of quality, so power, frequency, for instance, frequency control, or reactive energy control, etc. But mostly on the meter scale, so the units and the scale of the house, and the time scale of a minute to a week, basically, okay? Usually the energy management problems take some inputs. I've already told about that. So the loads and the weather forecast. We need to know in the following horizons what will be the consumption, and what will be the production, local production. So I will know how much I have to buy from the grid and how much I can store in my battery or in my storage system. If I have storage system, so it's energy storage system here, I will have to know the state of charge of my systems, okay? I will have to input some operational security constraints, like for instance, my battery cannot charge or discharge at a certain amount. Makes sense. Or my plug here won't handle this current or that tension, voltage, etc., etc. So those are operational and security constraints. And for those that were here yesterday and the day before, you already understand what's the constraints here in terms of optimization. Okay? We know that those constraints will be a real constraint in the optimization problem. Operational cost, this has to do with the objective of the objective function of our optimization problem. So basically, we need to know how much the energy we need to know the price of energy, but also the use of the battery, the use of all the devices that we have. Okay, some devices can actually have an operational cost which is not zero. And we have to know all the states of the system. So usually the main state of the system are the state of charge of energy system storage, but it can be other states. For instance, temperature. If you want to manage the comfort in the room, we need to know the state of it. Okay. That was for the inputs. Have you got some question about the inputs? Yeah. Pode ser em português.
No que se refere ao despacho das fontes de energias renováveis, geração distribuída, existe alguma norma com relação a quais os critérios a serem adotados para regular a quantidade que você vai permitir que despache ou não? Não sei se minha pergunta está clara.
Não. Desculpa. Não é clara.
Vou dar um exemplo. Vamos imaginar que eu tenho um conjunto de fontes de energia distribuída, eólica, fotovoltaica, e eu estou fornecendo uma quantidade X de potência. E em determinados momentos do dia, essa potência é mais do que a concessionária pode absorver. Os critérios para a redução da quantidade de energia fornecida para cada uma dessas fontes, existe algum critério hoje em dia?
Então, eu acho que algumas unidades de produção podem ser curtailed, yeah. Eu acho que não tem normas, não. Acho que vai depender muito do lugar onde você está, né? Da concessionária. Aí, na continuação desse exemplo, a gente vai fazer diferentes hipóteses. E essas hipóteses vão pegar a forma de limitações no problema de otimização. Então, a gente pode adaptar o problema de otimização a cada regulação ou normas de tal país. Por exemplo, na França, a gente tem um preço para comprar e a gente tem um preço diferente para vender quando tem muita geração distribuída. Mas tem limites. A gente não pode vender tudo, às vezes. Daí a gente vai ter, às vezes, que despachar energia. Vamos dizer. Mas tudo isso, todas as constraints, limitações do sistema, vão pegar a forma de constraints no problema de otimização. About the outputs, what are the energy management is made for? Okay, it's made for import or export energy from the distribution grid. Okay, so that the main purpose, but also dispatch energy in the grid, in the microgrid. Okay, so for instance, if I have a small amount of consumption and a lot of production, I can store this energy. Okay, so it will be responsible for this. And also, about the loads. Some loads are critical. We cannot touch them. Okay, for instance, in the hospital, we won't stop the machines because we want that, okay? In the hospital, or the servers of a university, we won't stop the server or turn off the server because we have a little bit less production of energy, okay? Those loads, I call them critical, so we cannot touch them, okay? But there are other loads like air conditioning, for instance, lights in some cases, or your washing machine, for instance. Washing machine, you can program it to turn on during a nice period, during the period where you have more production, for instance. Okay. So this is called shedding, curtail, and programming of loads. Okay, and we will show some example of this. That's the main outputs. Do you have other kind of outputs in your mind? Okay, if we go a little bit deeper, for instance, in the if we think about quality of energy, can you think about another outputs possible? The voltage balance, for instance, can be one of the output of the energy management. What? The forecasts are more an input. Yeah. So here there is another illustration of possible microgrid. And excuse me, here you will have to train your French. This is a French illustration. I'm sorry. But I will translate it. So this is the main distribution grid. There is a small distribution here, lines, transmission lines. Decentralized generation. So French is really clear here. Storages. Other kind of networks. It can be gas or heat networks. Here there is different loads, the critical ones, but also the flexible loads. Those loads that you can turn off or you can shift. And this is another load related to the house, so the light, the plugs, the heating or the cooling. So here in continuous black line, this is the electrical connection. In dashed line here, those are the controls. So there is a central controller here that controls the energy from the grid. It can control as well the energy storage, or it can control the flexible loads. Okay. And there is another small line here, which is the measurements. It needs measurements at any time to know what is the states and what, for instance, the production is at the time t. Okay. So here is the list of the functionality of what is energy management method. So the functionality is the forecasting, data management, because at every step we need the states of every unit, or energy system storage, for instance. Here there is a functionality of demand-side management. So the demand-side management is this method of curtail some loads, some shedding loads, or program loads. I have a mistake here in my presentation. And there is a functionality of energy management dispatch as well. And in this example, the dispatch is just the storage of energy. If we assume that the power is equal, yeah, there is only one control here. So we saw that there is different units in the microgrids, and we can consider all those units as small models. Okay, so the battery is one model, the house is one model, electrical circuits or thermal circuits. All the loads are basic profiles that can be shifted or curtailed, etc. And actually, Pyomo can handle this kind of block modeling. This is quite nice using Pyomo because we can just make a model of one battery, and once we made it, we can reuse it in another problem. Okay? So this is the structure modeling in Pyomo. And I do a small section about this. So what's the problem with math programming? So here you're not, don't read that, okay? It's not made for that. Okay? It is just that when the problem becomes bigger and bigger, and we have a lot of units separated and connected using electrical equations, for instance, okay, the problem can be tough to read and to understand, okay? And the mistakes are easy to do here, okay? We can really easily make mistakes. Here, actually, it's a unit commitment problem. So the minimization is the cost of all the power from the main grid. So it's a double sum because there is different generation and different time index. And those are all the constraints of the electrical network. Okay. And actually, we can define some blocks here. So there will be blocks on batteries, blocks on the network, blocks for the connection to the main grid, etc. If we look to the matrices of this kind of unit commitment problem, which is the same for each horizon, okay? We define different horizons one day, the day after, etc., etc. We have a structure block of the problem, optimization problem. And each block is actually the economic dispatch, and here it's the unit commitment. I will pass because it's a little bit, yeah, this one is nice. So if we consider multiple horizons, then we have one problem, electrical grid model at the time 0, at the horizon 0, but we have the same at the horizon 1, at the horizon 3, okay? So the same problems that is the same at every time step. It's just the data that are changing. And every block here, this is the electrical grid model. And in the electrical grid model, you can have the battery, the network, the house, electrical vehicle, etc., etc. So this is an object-oriented model construction, okay? So in Pyomo, to come back to the language, we can do this. The word block is actually a sub-problem of a bigger problem, okay? And it allows us to construct hierarchical models, and we will see an example in the following. So a block can be treated in much the same way as a model. So I call it a sub-model, but it's a block in Python. And we can add modeling component to the block. So for instance, the block battery, they will have their power, state of charge, etc., etc., and their own constraints. Block provide namespacing. Okay, so that's the way you can call block parameters or variables. So it's the model dot the block dot the variable dot the name or other methods. And here is it's the example of a block. A new block equal block, and you add a new block, a variable. Here you add a new parameter to the block, etc., etc. And here you have a bigger model, and you can add to the model the block, new block that we just created. So here it's the way you access a component with blocks. So it's quite straightforward. We can make a loop over the block. So it's not. So that's the solution of all the code that was printed before, and you can see it's quite simpler. If you want to go deeper, yeah. Now I will show you what it looks like when we have a real with a real example. So for the one that has Python that is working, you can actually look into it. So this is the Pyomo tutorial, and this is the microgrid problem. This is actually a problem that I wanted you to solve, but as you don't have all a computer, we will be doing this together, okay? So this is the summary of the microgrid energy management. The goal of the microgrid problem, here in this case, is to compute an optimal power flow within the distributed sources, loads, storage, and a main grid on a given time horizon. Okay? Here in this example, we will look at, I guess, 1 day in the following. Yeah, it's 1 day. The optimal powerful problems aim to find the optimal command of the components. So some of you can call it optimal. How do you call your problem? Kind of problem? MPC, model predictive control. In this case, it's charging or discharging the storage, selling or buying from external power sources, or turning on and off intelligent loads, etc. Does it make sense to you? You all understand what's the output of the energy management problem? You understand the problem, okay? Do you all understand the problem? Yes or no? Yeah? And actually this problem can be formulated as a mixed integer linear programming, as we saw in the really beginning, okay? Because if we consider only the powers, okay, this is just a unit commitment problem, okay? So how much is the power from the grid, how much the power I can store, etc., etc. So it's only linear, and it's integer because in some cases we will have to consider integer variables. So here it's an illustration in English, so I could have took this one for illustration. So here we have photovoltaics, battery, wind generation, etc., etc. Before handling this problem, we will continue with a little bit of theory. We will begin to model every components, okay? So the easiest components to model are the critical consumption. Okay, so the consumption of tomorrow, if I know it, will be up here profile in the time. So for the day, the following day. So my new variable, the critical power with respect to time, has to be equal to predicted power. Okay, so it's just an equality. We made a study with in Bamako, so it's in Africa. We studied an hospital, and they had a problem where usually the power grid here is really weak over there. Okay, they have shut down every day, multiple times a day, and as it's an hospital, they cannot handle that. They cannot have that. So they have a diesel machine, okay? And this actually costs not too much, but it's quite, there's quite a lot of pollutions based with diesel, especially close to the hospital. So we have a research project where we wanted to know if it was better to put batteries and energy solar systems. So we actually applied this kind of method to balance the two solutions. One solution with the diesel and one solution with the battery plus the solar systems. And we needed this conception of the hospital. But actually the hospital has a pretty well, a constant, I mean the profile is quite constant day by day. And in this country, they don't have a problem of winter and summer. So every day is more or less the same, except from Sunday and Saturday. So we added a lot of data, measurements data, so we could actually have access to this one. Okay, but that was the story to tell that in some cases we have access to this. I guess in Brazil it's the same. Here in João Pessoa you don't have a lot of difference between winter and summer days, right? You have more or less the same functioning. And when there is a lot of differences, for instance in the south or in Europe, we can take a basic day, like a day in the winter or a day in the summer, that makes a good match. So this is a little bit more complex problems. So the programmable loads are loads that has a definite profile, but we can just shift this profile in the time. For instance, washing machine, they have their own program, so they ask for the same power profile every time you turn it off and on. So we can program that using this kind of equations. So here the U is, do I turn off or on my machine? And it has to be integer, okay? And it has to only be turned on only once, okay? So the sum of U equal 1 over the time horizon, and U is defined on the binary domain. And the output power takes this form. So the P star is actually the normal profile, but it can be shifted here with the U variable. So in this example, I'm talking about a washing machine, but also charge of electrical vehicle or batteries. Sometimes the battery needs a specific profile of charging because of chemical phenomena, and so sometimes we can model the battery with these equations. There is other kind of programmable loads that ask for a fixed amount of energy. So here we ask for a fixed amount of power on a horizontal. But here we don't care about the amount of power, but we care about the total energy. So basically it's for some batteries that we just want to charge no matter what the power, but we need a certain amount of energy at the end of horizon. Okay, so we can model this with an integer over the horizon of the power that needs to be equal to a certain quantity. And curtailable is a load that I can just shut down at some point. So I can shut down the air conditioning when there is too much consumption. So we need a binary variables to say, okay, I stop my this source now. So it's defined between 0 in this in the binary domain, and it takes this form. The estimated power would be the power of the loads if not turned off. Okay? So in this case, it will be the air conditioning without being shut off. But it can be applied to lights, cooling, or computers, for instance. We have in our school a lab. Actually, it's a class for students, and it's all laptop. It's not computer with a big tour, etc. It's all laptop, and they are interconnected. And we are using the batteries of all the laptop to do this kind of systems. Okay, so when there is too much consumption, then we turn off the charging of the laptop, and they are working on the battery themselves. So we can actually manage the one room as a curtailable load. Okay. You have questions?
Sorry about the question, but about my area. But who provides these equations, these models?
These equations? Me. But they are quite straightforward, actually. And we will see in the actual, the final problem, we'll see them in Python. So for the aération décentralisée, for instance, photovoltaic panels or windmills, we have forecast that gives us the profile, the power profile in the horizon. Okay. So this is simple. Our variable for the power of the PV has to be equal to this profile that is forecasted. There are others kind of, are you doing some demand response methods? I shouldn't talk about this. There are other kind of models so available. For instance, fuel cells. They have a function. They have some other constraints for the functioning. Microturbines as well. They have some constraints. They cannot be turned on and off really quickly and really in seconds. It needs a ramp for the power, etc. So it's a little bit more complicated to model. The storage systems now. For the constraints of the storage system, this model is it's really simple. Okay, I'm taking a battery with this actually a power model. So I'm not looking at the voltage or current. So it's a first order or zero order model. The state of charge is noted E, like energy. And there is a first equation here that say that at the time 0, the energy in the battery is known and is written E0. At any time, the energy in the battery cannot be under a certain amount of energy, basically 0%, and has to be smaller than 100% or 80% of the state of charge, of the full capacity. Here, this is actually a differential equation. So this is not, but this is a linear differential equation, okay? So if we create a new variable, which is d over dt, which is actually, if we take, well, I will talk about later. So the variation of the energy in the battery is equal to the power charged times a certain efficiency minus the power that you discharge divided by a given efficiency. Okay? And this is a linear equation. Okay? If we would consider the current, the voltage drop, etc., it won't be linear anymore. Here in this case, you have, or we have, to add some other constraints. So we cannot charge and discharge at the same time the battery, okay? If we don't have these constraints, we would have some problems. And here it's the final amount of energy in the battery that is said to be equal to a certain amount of energy. Those are the constraints, but we can add contribution to the objective. Remember, I told about the operational cost of the energy management of the system. We could add some maintenance, replacement, recycling, investment cost from the battery. Okay, so we could imagine to express the cost, operational cost of the battery based on the charging or discharging power, for instance. Okay. Actually, there are some studies. I'm not talking about economical costs. Where there is some studies that say, based on the technologies of the battery now, the operational ecological cost of a battery is about 40 grams of CO2 kilowatt, which is quite high. So 40 grams of CO2 is not a lot, because when we deal with diesel or thermal machines, it's about 800, I guess, grams of CO2. So it's a lot less, but it's not completely a clean, let's say, it's not a clean technology. Okay, there is no clean technologies. In France, the actual ecological mix of energy in France is about 80 grams of CO2 per kilowatt hour because of the nuclear energy. I don't know about Brazil. Do you have some figures about the mix in Brazil? Well, you don't know the footprint, ecological footprint of energy in Brazil, electrical engineering? The amount of CO2 emitted per kilowatt hour. It must be good in Brazil because you have a lot of hydraulics, etc. If I'm not mistaken, and you have a lot of solar panels as well, right? But we can take into account the contribution of every unit. Okay, so the battery can contribute to the objective, if it would be ecological or economical. Usually when we have a battery, we like to add another constraint. This constraint is quite simple to understand. It means that in my battery, at every time, I want my battery to be able to be sufficient in case of the shutdown of the main grid. Okay, if the main grid stops working, I want to be working in my grid using my battery for, let's say, 2 hours. Okay, it means that at every time t until horizon h, which can be 2 hours, 1 hour, for instance. The power of the total microgrid must be equal, or here it's an inequality, but equal to the amount of energy in my battery. Okay, yeah, it's the comment here. In case of grid breakdown, the critical power will be entirely supplied by the storage over or horizon H. So if I take back my example of the hospital, it means that the battery must be sufficient to make the hospital work during a certain amount of time. Okay, this is how we write it. This is the reserve constraint. Main grid Now we want to model the main grid connection. As I said, there is a lot of different connection to the main grid. Okay, we have a different contract. We can have different laws depending on the countries, etc. Sometimes you can input power into the grid. Sometimes you cannot. Okay, sometimes you are limited to a certain amount of power, etc., etc. But the general form of the cost is the integral on the horizon of the cost of the power buy from the grid minus the power you are selling to the grid. Okay, this is a general case. So let's say that CG plus is the cost buying from the grid, and CG minus is the cost when you sell to the grid. Okay, there is a minus here because this usually is a money that comes in your pocket, right? Here the cost is in euro per kilowatt hour. It can be in reais per kilowatt hour, whatever. So what are the variables here? The variables are the power injected in the grid and the power buying from the grid. Here there are their definition domains. I prepared questions about this. Do you have questions about this equation? You all understand which term is it? Which term is it? You understand the terms? Okay. If it's a yes for everybody? Let's say if it's a yes for everybody. Can you connect yourself to the... Você pode pegar o celular, se conectar nesse endereço, uclub.com/ufpbp1. Tá bem na hora. Não sei se tu conhece, Fabiano. Tu já viu esse? Essa ferramenta é um aplicativo do celular. Tu vai na internet e tu pode responder umas questões assim. Conseguiram se conectar? Conseguiu? Pode fazer com o computador também. Dá para fazer com o computador também. You understood the question? Everybody understood the question? The question is, actually, this is the general form, but depending on the value of these prices, the system operator gives some prices, it sells and buy energy at a certain amount of price.
Plus is how much you consume.
So the plus is the buying, yeah, it's the buying from the grid. And the minus is when you sell. So there is one policy connected to one value or
What does it mean?
não existe meu bem. Não existe meu bem é this is a policy that doesn't exist. This was the funny one. Obrigado, professor. Tudo bem? Conseguiu se conectar? Conseguiu? Se não fazer no aplicativo, só na tua mente tu faz para ver se tu consegue. Quer mais faz grosso, assim? Só me falar quando você acha que mais ou menos você conseguiram a resposta certa. Tu fiz?
Eu botei B, D, A, E, C.
Vamos ver. Não me lembro de cor, mas vamos ver. Já temos 5 respostas. Mais um pouquinho. Mais um pouquinho para cá. Conseguiram fazer? Mais um pouco? Vamos ver os resultados? Ou ainda um pouco mais? Vamos ver os resultados. Oba! Então, só 44% para... Então, vamos começar para mais alto. Então, aqui se o custo, quando você compra da rede, é positivo, isso é normal, né? Isso é clássico. Mas se o custo de quando você vende para a rede fosse nula, zero, quer dizer que essa polícia não está não encoraja o investimento em gestão distribuída. So that's clear.
Fui reprovado. Quero fazer reposição.
Pior que eu vou ter os nomes das pessoas que estão reprovadas. In this case, they all are positive. So it's normal, okay? It makes sense. It means that it can be a profit. You can have profit with selling your energy. So it's actually encouraging investment in distributed generation. But it's also encouraging the self-consumption, okay? Because here, when you buy for, it's more expensive than when you sell. So it's better if you have a lot of consumption if you have a lot of production, local production, it's better to consume yourself, okay? You are minimizing your bill doing that. In this case, there are two positives, so actually it's another case. Here, it's better every time to sell because the selling price is bigger than the buying price, okay? So when you want to consume, it's better to sell and to consume from another source, okay? So it's also encouraging investment in distributed generation, but it's better, okay? So this case is actually this one that's inverted, and it doesn't exist, right? Because it means that when you buy energy from the grid, the price is zero, so it doesn't exist. But it means that they pay you to produce, but you don't pay to consume. So it doesn't exist. Não existe, meu bem. The last one is actually doesn't make sense as well, because you are buying energy from the grid, but you're also paying them when you introduce power in the grid, okay? So they are penalizing selling energy to the grid, okay? So this one is, actually I don't know if it can happen, but it may happen if there is a lot of congestion on the grid. Okay, do you have questions? So who succeeded? Lucas succeeded? Yeah. Okay, that was linked to your question, I guess, Fabiano, because it depends on the policy of the grid operator to fix these prices. Imagine that you cannot sell energy to the grid. It means that this value will be always zero. So it means that this PM, small PM, is zero. Okay. So it's actually a general form that you will be working for any circumstances. Here I wrote the contribution to the cost for ecological assessments. It has the same form. Here you can find the CO2 mix of the grid. So basically, or in France, it's 80 grams per kilowatt hour, but it can be different, or it can be dynamic as well, depending on the time of the day. So there, it's indexed by the time. And here, this is the mix of your own electricity. Okay. So if you have, sorry. So if you have windmills or solar systems, you can here add your mix, ecological mix, taking into account recycling, investment, or construction of your devices. You can, of course, have both. Okay, so you could have a big contribution of all the two, a big objective of the two. This is linked to the question. Here I'm illustrating the objective here, the value of the objective, with respect of the power to the grid. So here, this is the power buying from the grid, and this is the power here selling to the grid. Okay, so this is the form of the objective, of instantaneous objective. Okay. Actually, it's the form of this. If the prices are different, then you will have one section here with the given price and one section of it with another given price. And here you can see that this instant cost is convex. Okay, you see, you remember the first class when I told about the importance of convexity. Here we see that the objective is convex, so this is a good thing. Okay, it will be simpler to model. And we only need, so it's convex only if the buying price is bigger than the selling price. In this case, we don't need binary variable. We just define one line here, and it's okay. There's no problem. If this is the opposite, if the selling price is smaller than the selling price, the objective function is not convex anymore. Okay, so we need to integrate a binary variable that will tell when I'm buying, when I'm selling. Okay, otherwise it doesn't work. To do that, I just had some couple of constraints that say, here I have my binary variable that say that if I'm selling or if I'm buying, and here I have some new constraints that say that my buying power should be 0 if U equal 0. You all got that? It's not that easy to understand when you see the equations, but actually it makes sense, because if we don't put this, the optimization algorithm will sell and buy at the same time. Because if the selling price is smaller than the buying price, it will sell the maximum and buy the minimum, and it will earn money, but that makes no sense, okay? So we have to put those in this case, in this particular case. Remember about the objective function. So we told about the objective function of all the different units, all the different blocks of our main grid. But we can now add all this operational cost, and we have a final objective that is like that, okay? The contribution of the grid, the contribution of the energy storage systems, the contribution to the production, etc., etc., okay? And we can have a lot of different units. This can include, for each component of the microgrid, investments, maintenance, replacement, but also ecological costs, social costs, etc., etc. Okay. This is a slide that we already saw. When I have different types of objectives, for instance, ecological and economical, I can balance them using the weighted sum and the epsilon constraint sum. You do remember the two methods? Well, if you don't, just look at the first slide. Bora fazer uma pausa? A formulação do problema, né? Daí essa secção é justamente um projeto que deveria envolver todo mundo, tá bom? Então eu queria mais interações, mais questões, mais sugestões da parte de vocês. Se você quiser, você pode acessar o Python, como eu já expliquei ontem, usando o site que eu provisionei. As pessoas que não têm computador ou que só querem continuar comigo, tudo bem. Mas eu vou pedir um pouco mais de interações. You all remember the initial problem of the energy management problem, right? Energy management of the microgrid. Para quem quer seguir, é no PyMO tutorial, and the problem is the microgrid problem. Here, this is the version 0, because it's the simplest model and simplest problem we're going to solve. Okay? So here the problem statement. The energy management problem can be formulated as a mixed integer linear programming. This we already know. So the plan of this example is first the definition of the sets. The sets are the possibilities and the time in our case. Secondly, we will define the sources, the storage, and the loads. Okay? Finally, we will define the constraints of the network, and then the overall objective. of the energy management problem. Tudo bem? Make sense to you? Faz sentido? Então, primeiro, essas duas linhas a gente já sabe o que quer dizer, né? A gente está importando as funções de Payomo que a gente vai usar. Isso a gente já viu. Aqui estou definindo o horizonte de tempo. Aqui estou pegando um dia e H aqui é exprimido em segundas. Daí faz essa quantidade. Primeiro, eu vou definir um problema vazio, que se chama M aqui. Segundo, eu vou definir o tempo, que é aquele horizonte. Entendeu? Então, e se eu faço Shift Enter, essa vai ser feita, tá bom? Para quem quer seguir ao mesmo tempo. Por exemplo, eu posso fazer m.time com print. Print. Então aqui o tempo é definido com a dimensão 1. Ainda ele não tem size. A gente vai ver por quê. Porque ainda não é construído. E agora vamos chamar os blocos, que são as baterias, the main grid, the sources and the loads. The microgrid is created by connected units together. So the units that we already created in my library. So the battery, the loads, the renewable sources, as you know. So here it's like a description of the first version of my microgrid. It's a really simple microgrid with only one connection to the main grid. That's obvious. One renewable source and one load. Okay, so this is a really simple example. I have one solar panel or windmill. I have one load and one connection to the microgrid. Let's have a look to this, the three models. Here in this example, I gave you the models of each components. They are all available here. So for instance, the main grid is here. So the main grid is defined here. Here I have my documentation. And here I define the model, the problems, okay, of the main grid. And we can, and this is actually what I just presented to you before. Okay, we define variables for the charging and selling and buying of the energy. We define here a cost. We define parameters, which are minimal power and maximal power. And we define constraints. Here, this is the constraints for the maximal power. This is the constraints for the minimal power, etc. Let's see the model of the battery. Here, the battery is defined as a block. Again, here I have some documentation. This is a really simple battery with limited power output. And we can fix the initial and final storage energy. So it is the same model than I have presented to you in the slides. So you have one variable, which is power. I have one other variable, energy, which is indexed by the time. I have some parameters, which is the minimal energy, the maximal energy, initial and final states. So this is the same notation than I showed you in the presentation. Maybe I can open it at the same time. Yeah, that's better. So you recognize here, the scope, the power, which is the same here, the energy, which is the same here, the charging and discharging parameters, which are by default equal to 1. Now, this is best if I put this in the middle, right? And I have to define some derivative variable. This is the first time here we saw the derivative variable in Python. It's when you have differential equations, we need not to define only variables, but also derivative variables. Here, in the presentation, if it wants to show up, I had differential equations, which is the variation of the energy in the battery is equal to this quantity. To do that, I have to define the derivative variable, which is a variation of the energy, which is a variable here, with respect to time, so to the index time. And here I also declare a derivative variable of the power. I don't need this all the time, but in the following, I will want to limit the variation of the power of my battery. So I need to define it. Okay? If I want to limit the variation of the power of my battery. Okay, those are the constraints. So you recognize, as we saw yesterday, how to define a constraint in Pyomo. This is a simple function that returns an expression with variables, an equality sign or inequality sign, and another expression. So here 0. It means that here the power at the initial time must be 0. Here the energy in the battery, so energy initial, if t equals 0, then the energy at the time t must be equal to the given parameter E0. I'm not going to describe all of them, but you understand the idea. Here are all my constraints. Here I created a constraint for the variation of the power, the maximal variation of the power. And here I created my constraint that said that the variation of the energy is equal to the power. Okay. I created all the functions, and I need to add those functions as a constraints to my model. What do you have questions for the battery model? So we saw the main grid, we saw the battery. The source are quite easy because, as we saw on the presentation, source are just a given profile that we follow. Okay, so it's quite easy. I don't know if I have different sources, PV panels, for instance, are here. I'm not going into detail. So I can actually import those models, all the models, which are blocks. I add them to my model. I give them the name, so my model that my main grid, model dot source, model dot load. Okay, makes sense. So this is nice in Python because once you have your model done or written somewhere, you can add them and construct step by step a new problem. So here I can do that. So here I know that it's done. So I can print my new model. So if I ask for Python to print the model, it said that my model is created with 3 blocks. One block is called L, which is the source unit. One block with the main grid, and another block with source unit. And for each block, you have another description. Okay. So here, the source unit, you have 2 parameters. The actual power. Oh, yeah. Here, the main grid, you can recognize the cost parameter. There is parameter for the maximal power, minimal power. There is one variable, which is the actual power you exchange with the grid, etc. Do you have a question about this this block? So it's quite easy to understand. I just created a model. I'm just adding small unit to the model, but we didn't. For the moment, the blocks are independent. Okay, we need to make a connection between each block. To do that, we have to add a global power constraint, which says that the sum of all the power of all units must be 0. Makes sense, right? It said that the sum of the power of the sources must be equal to the sum of the power of the loads. How I do that? I just have to create a constraint that say, here at every time t, the power of my main grid plus the power of my source must be equal to the power of my load. Okay? That's the general constraint.
So the first term is M and G. Return M and G. This is what power?
mg is main grid power.
Okay.
This is the source power, and this is the load power. If you want to see that, for instance, we can ask to print m port mmg. The print. This asks to print all the model, all the block mg. So there is a documentation, simple main grid unit, and inside this block there is one variable called power. Okay. And here you have a source. It's a source convention. It means that it's positive when it comes into the main grid. For instance, the load, if we want to see the load, he has also one parameter p, but normally it should be here p, the power, which is fixed, so it's a parameter. There is no here the documentation is not done, but normally it should be done. Então a gente baixou esses modelos, a gente juntos num modelo mais grande e a gente fez uma conexão elétrica escrita aqui com power balance. Agora o que precisamos fazer é definir o objetivo geral do nosso problema de otimização. Como eu falei na apresentação, poderia ser econômico, ecológico, sociológico, muitas coisas. E cada das unidades de potência poderia ter um objetivo e todos iam se juntar.
Uma pergunta, eu posso definir mais do que um objetivo?
Não. Como a gente viu no início do curso, é que aqueles problemas que são determinísticos e aqui são Mixed Integer Linear Programming. Então, são tipo de problema e tipo de solver que só vai encontrar um objetivo. Mas, se tiver num problema vários objetivos, por exemplo, se tiver econômico, ecológico, daria para fazer ou uma soma ponderada, por exemplo. Por exemplo, na Europa, o preço da tonelada de gás CO2, como se fala? CO2. Gás carbônico. A tonelada de gás carbônico é mais ou menos 85 euros. Daí dá para juntar finalmente e pegar só um objetivo. Entendeu? Quando não dá para fazer isso, a gente tem outros tipos de metodologia que faz que no final tenha só um objetivo. As the first hypothesis, because it's a simple example here, this is the first stage of example, I'm only considering a fixed selling and buying price, okay? So the C plus and the C minus are equal, okay? So it means that my objective function is the integral from 0 to the end of the horizon of C times the power of the microgrid at every time t, okay? You can actually write integral using PyMO, okay? And this is done like that. So I create an integral expression which is indexed by the time t, and which is the sum of the instant cost of my microgrid with respect to the time. And in here I say in the second line, the objective of my problem is this expression, is this integral, okay? So I can desculpa, eu até com dó de cabeça aqui. If I want to, okay, there is another step that I didn't talk about. It's for the moment, I created a time horizon, but I didn't said which time step I'm considering, okay? Because I just wrote differential equations with the variation of energy with respect to time, and I didn't say what's my time step, okay?
Só para retornar essa questão da questão objetiva,
Sim.
Algo que me deixa bastante curioso é o seguinte: eu gero energia a partir de uma fonte fotovoltaica. Hoje no Brasil a gente só tem a tarifa, estamos criando agora a tarifa branca, que é um horário diferenciado. Quer dizer, para mim uma questão que vai ser importante é definir se vale a pena eu consumir a energia, armazenar a energia ou vender a energia. Então, nesse caso, eu poderia juntar todas essas três hipóteses numa função custo.
Sim.
Correto?
Sim.
Interessante.
É isso que vamos ver. Isso que vamos ver. O que ia falar? Agora, nosso problema, a gente não definiu os dados e a gente não definiu esse time step. Só as equações diferencial. But if you want to actually solve the problem, we have to define a time step and to solve the problem over this time horizon. To do that, we have to instantiate the problem with the given data, discretize the problem, so the differential equations, usually we have to discretize it, and at the end we have to solve it. So this is this part. M here is an abstract model. It means that for the moment I didn't define the parameters. All the parameters in my model are not defined. Which means that the structure of the problem is now completely defined, so only the structure. And may be used for different scenarios. Okay, so we can take the same problem with different day, different scenarios, different price profile, etc. Which is nice if you want to use the same model for other cases. So now we are following the following steps. First, we are going to load the data, which are in the data folder for the people who wants to follow with me. We will be instantiating the problem, discretizing the equations, and solving it. Okay, so let's have a look to the data. This is here. Okay, it's a little bit complex because I have to look for Excel file. I have to read the Excel file, charge it in a workspace, etc., etc. So I'm not going to detail, but basically here the most important if you want to change the day, etc. I took a first day, a T start, so the time at midnight, the 18th of February 2019, and I'm ending my horizon one day after. So here I read my data, which are here. So here I have my data for actually a lot of days because it's a real building. So I have measurements for real buildings. Here I have my consumption. It's the global consumption, the consumption for one room. Pmax, it's the power from the photovoltaic, so it's the forecast of the photovoltaic power. This is not used, I guess. I guess it's a wind speed if you want to put a windmill. And this is a CO2 emission mix of the energy. So here I run my the data. I'm just loading the data. I can print them if you want to, though. Yeah. So in this particular example, I choose one day in February. And the PV generation is that form. So you recognize the PV generation during the day. And I have a consumption that is quite constant. And you can see there is some periods where I have more consumption than production. So it's one typical day in the winter. So here it's just to create an actual problem using the data I just loaded. And now I want to make a discretization, let's say, every 15 minutes. If I do 15 minutes for a horizon of 1 day, it means that I need this number of finite elements. Okay? Here, this is a Pyomo function that will take my model and make the discretization. Okay? So the differential equation, the variation of E. Oh, can I have a pen, maybe? Ou é para caneta, se tiver.
Eu tenho a caneta, se eu tenho.
Ah, tá aqui. Obrigado. Eu tinha definido essa equação. If we suppose that there is no efficiency, or the efficiency is 1, etc. And now this line just creates this equation, and this equation is linear, okay? So this is a simple Euler, do professor Euler, que inventou isso. Isso é bem simples, mas na verdade existe várias. It exists a lot of different scheme. Okay, so we can choose a scheme that is more precise, etc. So it's just a finite difference. Once I made the discretization, this will be a little bit more nicer to print. Oh, whoa, 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 whoa. Now I have my equations. So it's a little bit, I have discretized every 15 minutes of 1 day. So I created a lot actually of constraints because there is a constraint every time step. And my objective function is a sum at every time step. So the equation I'm building here are huge, okay? So here this is the expression of the integral of my problem. As you can see, it's big, okay? But the nice thing with Pyomo is that everything is automated, okay? I created only one equations, I defined it the time step, and you create this linear expression itself. So the objective is the sum of all this thing here. It's the integral here. Here it's parameter. Here it's the time declaration. Here is for the main grid. We have one parameter which is p, and is defined from time 0 to this value. Instantaneous cost, it was the instant cost, it was the cost of the energy at every step. So here this is the expression. As you can see, it's a big problem. So here it's a constraint that I called P max. Let's say the lower bound of my power is actually minus infinity, and the upper bound is a parameter. This is the constraints on the minimal power. Okay, the model is really big, so I won't. And now this is the solving step. That's done. Okay. And this is the post-processing. Okay, the terminal condition is optimal, and it solved the problem in some milliseconds. Professor Fabiano, eu não estou sinto muito bem, eu acho que eu vou no banheiro rapidinho.
Ok.
Pode ser?